to quickly introduce Paige. So Paige is a support scientist in the Office of Chief Science Data Officer at NASA headquarters. She envisions a future with inclusive, transparent, and robust scientific research, and believes that open science frameworks are the best tools to achieve this vision. She did her PhD in physical oceanography at the University of Michigan, and her postdoc in climate data science at Columbia University Lamont Doherty Earth Observatory. She brings years of scientific and technical expertise in large-scale data analysis, open source software, and cloud computing. She is also a steering council member of the Pangeo and open source science communities and has led hackweek and capacity development events in several countries. Paige, so glad you can be here and speak about your work.
Yeah, thank you. Thank you very much. It is really fun to be here. You may have seen the title of my talk as Challenges and Opportunities in Open Science, and it is a very broad title. And in all honesty, it's because I couldn't decide what I was actually going to talk about when they reached out to me a couple of weeks ago. I said, well, I don't know, I'm just going to have to give a broad title. So I've tried to give a subtitle here to make it make it a little bit more clear what I'm going to talk about, but I'm going to kind of cover a bunch of things. So I'll talk about NASA's open initiatives. I'll talk about some of the open science communities that were just mentioned, and also just kind of the changing landscape of how we are doing science. So as you can tell, my lens is from science. That was my background. I'm actually going to start by kind of giving you a little bit more information about my background, because I think that's important for framing what I will be talking about. So in a good science project, we always kind of state our assumptions at the beginning. I feel like this is kind of me doing that so that you know what my assumptions are. And as we've said before, there are a lot of terms. I'm going to say open science. That tends to be what we use at NASA, although we interchange that with open source science. There's also open scholarship. Since NASA is a science agency, I'm going to mostly stick with open science, but many of these I will use interchangeably. Okay. So as was mentioned, my background is in physical oceanography. I made plots like you can see over there on the right. These were idealized models that there was meant to be an ocean basin, and you can see there are no coastlines. My oceans were square. It was a very lovely world to be in because my data was very neat. In my postdoc, I did climate data science. So I worked at the intersection of climate research and data science. So really more interested in a lot of the software and infrastructure tooling that we use to do science. And I worked with much more realistic global climate models, like here, which looks a lot more, you can see that I'm plotting some data in the global ocean. It's no longer just a square. And of course, now I'm at NASA. Basically my job is to kind of help enable and support open science, specifically for the NASA community. I will also mention that I will talk a little bit about NASA, and you'll tell which slides those are, because those are the really nice ones where I use NASA templates. The ones that look less nice are the ones for me. And I will say that like when I'm kind of taking the NASA hat off, because as Spot was just saying, there are a lot of things I will say that do not represent NASA, but are my own personal opinions. Okay, so I like to talk about kind of how I was guided into open science, open source, because I think these are kind of, I guess this is the framework where I'm coming from. So the first one was the idea of kind of accessibility to tools. And I had basically, I lost access to MATLAB, which many of you may know, great tool, but it is not open source. You need to have a license to use it. My undergrad did have licenses for personal use. So I had on my laptop, I had MATLAB, so I was using it there. I then did a year in Germany between undergrad and grad school. I was at a university in Berlin, really fun, but they did not have personal MATLAB licenses. They did at their library. So for a while, I was taking some classes where I needed to do computing, and I was traveling across the city to go to the library so I could use their computers. So I guess this really isn't I lost access. I think this is more about me being lazy. And I was like, gosh, this is really annoying that I have to go all the way across town to get to the library just to do my work. And luckily, I had some very clued in German colleagues who were like, you should take this year to learn Python. And I did, and I've never looked back. So that was really my first step in this direction. The second one is scalability. So fast forward, really kind of at the end of my PhD and then starting in my postdoc, these open source community-led tools were the ones that were best for handling really large and complex data sets, which I was doing in my research. So I was using data from climate models. These tend to be very large. These models turn out a lot of data, and they're also very complex. They're multidimensional. We have multiple variables. We've got our latitude, longitude. It's mapped onto a global grid, which is hard to do on a sphere. So there are all these complexities to it. That equation under there, you don't need to know what it means, but it's just to say this was just one of the equations that I was doing in the actual analysis and the computation steps. So it's a very complicated process. And I spun my wheels for a while before kind of landing in a group, the Pangeo community, which I'll talk about in a moment, that really helped me understand kind of what the problem was and how we can go about using this data effectively. And the last one is kind of inclusivity side of openness. I was very fortunate to really see firsthand how open source and also free, the fact that these are free is a big one, software removed barriers to doing science. And I have a story that I want to tell about this. So this here is Mumin Oladipo. He is just finishing, I think even this month, his PhD at the University of Ilorin in Nigeria. And while also finishing his PhD, he already has a lectureship at Koladaisi University in Nigeria. I met him through the Coastal Ocean Environment Summer School in Nigeria and Ghana. We actually have updated the name since I made that slide, or for short, COESing. This is a really incredible program that I've been really fortunate to be involved with, and now I help organize it, and I'm the lead computing instructor. We go to Ghana and Nigeria so far. We have an in-person, we actually are hybrid now, school where we're teaching topics in ocean science and environmental science. And now I've started this big computing side, which is one of the most, I'll just toot my own horn, the most popular tracks that people do right now, which is really fun. And this has developed over a few years. Now we've got a whole team of Python and other open source instructors. But the story that Mumin told me was a really interesting one. So he came to our school in 2018, which is the first time that we introduced Python into the school. We had been using MATLAB before because that's what the instructors knew. And he was one of the small group where we kind of piloted this project. And then he came back the next year, and this is a quote from him. He wrote this to me and said, "Oh, I'm using Python. It's so great, and let me tell you why." So I'm just going to read a little bit about of what he said because I think it's really interesting. So instrumentation is a challenge in developing countries because of poor power supply, technical know-how, and access to sensors and other components. So research is being impeded. Upon learning Python at COESing, I was able to construct a reliable, very low frequency receiver to collect solar flare data for my PhD work. The Python language was useful while setting up the device, and the device has been taking data for almost a year. It's actually been about 5 years now. Hitherto, I was using a desktop for the data collection, but the desktop consumes about 300 watts, which was beyond my budget for power backup. Consequently, the Raspberry Pi setup solves the problem of power. It consumes less than 10 watts. Therefore, our budget on power backup was sufficient. And the project was a success. And he's actually gone on to build a lot more instrumentation at other universities in Nigeria, which is part of what led to him getting a lectureship while still finishing his PhD, which is really impressive. So basically, what I think this story is really incredible because we talk about being open, making sure that we're inclusive for everyone being able to do science. And here, the barrier to Mumin doing science is not what I ever would have thought about from my own background. It was the cost of the electricity to power the instruments that were being used. And so before he knew that Python was a tool that he could use, the only thing he knew about was Excel, and that had to run on a desktop. So he had to power a desktop, but he couldn't afford it. Once he learned about Python, he then started reading. He said, "Oh my gosh, there are these small computers, Raspberry Pis. I can program that with Python." And so it was this open source language that enabled him the flexibility to use different tools that he could afford. So I just think it's a really incredible story and really speaks to the power of using open tools. So those were the pathways kind of guided me to open science. So I say I came for these benefits, but I stayed for the community. And what community do I mean? There are a few communities I've been part of. Pangeo is one of the big ones. We call ourselves a community for big data geoscience. We have a lot of things that we're kind of focusing on. So here we're kind of obsessed with efficient data processing. This is where I was talking before about my data being very large and complex. This is where I found a lot of other people dealing with the same issues, and we are developing tools to make it feasible to actually process the large and complicated data sets that we are working with. And so we're also all about open source software. We kind of build everything that we do is pretty much based on Python at this point, Xarray and Dask and Zar, Jupyter notebooks, all of this kind of thing. And then we have an infrastructure. So we've really, as a community, pushed for more cloud-enabled science. And I'll talk a little bit more about that later in the talk. I'm also part of open source.science, another community, where the goal is to really bring together scientific users and software developers together to accelerate science. So we have some kind of interest groups that are kind of across the scientific disciplines, and then a few that kind of cut across all of those disciplines, like talking about reproducibility and mapping in science, which I think is a really cool idea, and I will also mention that a little later. Ocean Hack Week is another one I've been involved with. Basically, it's what we all think of as hack weeks, trying to promote good computation and analysis workflow best practices when dealing with ocean data. So these are all kind of some of the communities that I've been involved with, which is why I've really become a champion for open source and open science, because I absolutely love these interactions and I've learned so much and has enabled my work. Okay, so I'm going to talk just a little bit about what we're doing at NASA in space. This was mentioned at the beginning and part of why we're having this. This is a year of open science, 2023. It was announced by the White House. This was mentioned before. There are now 16 federal agencies that have signed on, which is very impressive, and that number keeps going up. My slides keep being out of date. But it's not just the federal agencies, as we know. The UC campuses are involved. There are a lot of other universities and organizations as well. Okay. We always like to have a few examples of kind of open science in action, and just to give an idea of what we're talking about, especially through the NASA lens. So this is one of my favorites. It's about how kind of making our data more openly accessible can enable new types of science that we don't even think about. So this image here is of some NextRad radar data. This data is, it's from NOAA, the National Oceanographic and Atmospheric Administration, and it's been used over decades to track meteorological phenomena, weather patterns, that kind of thing. And back in the day, it was stored on physical tapes because that was the only way to store things, previously. So more recently, they digitized it and they put it on the cloud. So it's more accessible to more people. And what they found was communities outside of the ones that they were in, the weather and meteorological communities, were finding use in this data and doing really interesting studies. And so one of them was the kind of bird research community, where they looked at the specific bird called the purple martin that could be seen in this data set. And that's because they do this roosting pattern where they have tens to hundreds of thousands of birds that do these like really incredible aerial displays in very small locations. I really like birds, if you can't tell. They are really fun to see. I don't know if they do them around here, but it's like a whole thing in Austin, Texas, around SciPi, where I've seen a few people here. It's like they have like booths set up. It's like a whole festival. But because of that, there's so many birds in a small space that they are being reflected, and you can see them in the radar. And so they can actually study the patterns of these birds and how that's been changing over time, and how that's related to various climate changes and stuff. So I think that's a really cool example of enabling new science. Another example that's really on the side of kind of collaborative work is this is an image of the James Webb Space Telescope, which many of us are probably familiar with. It's been sending back these stunning images of space. They did an early data release, which was planned. They were like, we were going to release some of this data early to kind of, see what discoveries we get, to get some excitement. And the scientists who are responsible for that said, let's see how much we can get out of this early data release. So they ended up bringing in, they kind of invited anyone who wanted to. It was like hundreds of scientists who worked together. When they first pitched this idea for the early release, they were like, yep, we'll get a handful of publications. It'll be great. They ended up getting over 40 publications in a very short amount of time. And one of them in the corner here showed our first evidence of carbon dioxide on an exoplanet, which is why I have this kind of catchy title, the first step toward discovering life on another planet. So we need carbon dioxide to have life. We have not found life, just so that's clear, but maybe we're one step closer. So anyway, some really cool discoveries that came out of this really collaborative work in such a short amount of time because it was done in an open way. So NASA is really trying to, encourage more of these types of open collaborative projects. So we have the Open Source Science Initiative, and it kind of has 4 pillars. So we're looking at what infrastructure we need to really enable all of this. What policies can we put in place to guide individual researchers in knowing how to be open? And of course, funding is a really big one. How do the funding structures need to change, or do they, in an open space? And I could talk a lot more about all those, but I'm not going to right now. Happy to talk more about those later. And then there's the community side, which is where NASA's Transform to Open Science initiative comes in, or TOPS. This is a 5-year initiative to accelerate adoption of open science. So we're working across a lot of different areas. One of the big things that we're doing is developing an introductory curriculum for open science, which we're calling Open Science 101. It has these 5 modules, kind of roughly following a scientific workflow. And the idea is to give everyone kind of the base vocabulary and kind of understanding of what open science is. So this is not going to provide a lot of the technical skills or knowledge that a lot of us might be familiar with. This is really more on the kind of helping to change the culture around how we are doing science. So if you haven't noticed, we do love our QR codes at NASA. So here's another one. I should mention, OS 101, this Open Science 101 has not been released yet. We're hoping to release it in December. And it'll be a first version. We'll be looking for community input. So it is a community developed curriculum. Some of the specific, one of the main goals is that we would like people to come out with a better idea of how to write their data and software management plans. NASA has this new one that we're calling the Open Science and Data Management Plan. So it kind of covers a lot of the open science process. And you will get a little NASA digital badge if you complete this. So anyway, in case that's of interest. Okay, so that was the NASA side, just so that you're all gonna know what NASA is doing. Now I'm gonna take my NASA hat off. I really wish I have the shirt. I don't have a hat to actually take off. That'd be pretty cool. And I'm just these are kind of some musings and some ideas. So, if they're interesting, great. If they're not, that's okay. Hopefully you don't boo me off the stage. So I'm gonna kind of talk about the open science landscape and how I see it and how it might need to be changed. So first, I'm going to say, I think in many ways, not all, but in many ways, open science is really what science was set out to be. But in the past, science was constrained. So what do I mean by that? For instance, computing resources were scarce in the past. If we're talking several decades ago, people didn't have their own computers to do their own computing. So if they wanted to do computational science or any sort of computational research, they needed to go to a physical institution to have access to these computational resources. So a couple examples from kind of the early days. In 1952, the first computer owned and built by an educational institution was established, called ILIAC at the University of Illinois. It's where I grew up, so that's kind of cool. Another example is in 1963, NCAR, which is the National Center for Atmospheric Research, got their first supercomputer. Now, of course, the term supercomputer is relative because those were a lot less powerful than all of our smartphones, any individual smartphone today. But I mentioned this in the NCAR one because now in the climate community, NCAR is viewed as one of the facilities that has one of the biggest computational facilities. They have a really great HPC system. So anyway, computing resources were scarce. And really, things have changed a lot since then. It was also very different. This was mentioned in the keynote earlier this morning. How we disseminated scientific knowledge was very different then. We had to rely on physical journals. And so these kind of necessitated having access to institutions to get into the library where the journals were physically delivered and put on shelves so you could go and access a physical journal and find the article you want and read it. I also mentioned another example earlier of how we store our data. It was on physical tapes. It's much harder to access when you need to kind of be in a physical space to get it. So this is very obvious. We are now in a very different world. We're in a digital world. We have computers, we have the internet, and these were really huge advancements in society and has changed a lot of how we're doing our science. Part of this is that we have less of a reliance of a kind of being physically situated at various institutions. And I'm kind of saying this because I'm getting to a point later, but I think this is really changing how we can do science and what potential that we have doing science and doing scholarship in general. I will also argue, I think the advent of computers and the internet really shaped our society. I don't think that academia in general has changed as much as those aspects have changed our society. And so I think there is a lot of kind of catching up now. And but anyway, I'm not really going to talk more about that. But they obviously did change a lot of how we're doing our science, and they changed a lot of the science that we're able to ask. Now we're doing these incredible climate models and analyzing this. So we're changing how we're doing our science, and there's now this real paradigm shift in how we are doing science or research in general. So kind of going along with what I was saying before, how we kind of have these, you needed real links to kind of physical institutions in the past to get access to the tools and infrastructure that we needed. I think in the past, we had these different universities, institute, agencies, kind of all of these, I'm going to call these like institutions. And we had a lot of the funding and the policies that were really dictated from the top down from each of these institutions. And I think a lot of this was needed because this was, they were the ones that had the computational facilities. So they're saying, okay, we have a supercomputer, you need to apply for the time. Here's how we're going to do this. Here's the policy that we're putting in place for how this is done. And of course, I have these smaller arrows that are showing there's always been collaboration across institution. That's kind of been a foundation of academia. But I think there was less of that before. Of course, the digital world makes it a lot easier. But what we are seeing more of now is these kind of cross-cutting grassroots communities that kind of cut across all of these institutions. And these include like open source software. A lot of the software, same software is being used across all of the institutions, infrastructure, and these open science communities are really at the core. And these tend to be grouped around scientific discipline, the structure of the data that we use, and the types of analysis that we are doing. So I'm mentioning this because I think in the past we've been largely siloed in these institutions. And what we are seeing is that the communities are speaking up. I mean, people like us saying, like, we really need to work more across institutions. And communities are starting to do this on their own, saying, well, we don't like, the current landscape for how we're doing our computation. We're not able to do our science, so we're going to create our own system. And we're seeing more of these that are cutting across. I think because, like for me, I found the Pangeo community, which happened to be using the exact data sets that I was. So I found a community based on the data. And that was really important because very few people at my university were using that type of data. Now, there are all sorts of great people at my institution, but that's not where I was getting the help that I needed. And so I'm going to talk a little bit more about this later, but I think to me, these open science communities cutting across institution, I think is really important and is something that, as funding agencies, talking to myself, we really need to make sure that we are supporting these community actions, because it's really what the community is speaking up and they're saying this is what we want. Yes, I forgot to put this in there. So one example that I'm going to show, kind of the community being like, we want a new model because what we have is not working, is going back to the Pangeo community and how we're doing our science. So now I'm going to get more on the technical side. So this is, I claim no credit to this because I did not join Pangeo until after all of this had been decided on. But the early Pangeo community was like, the way that we are currently doing our science is not feasible for us. So what we currently do is we download data from, data is stored on a server somewhere, we download it, whether that's to our personal laptops or our university computing system or somewhere where we can do our computations. This works really well. If you have megabyte-sized data, this is great. There's no problem. Don't even have to think about it. If you have gigabytes of data, it's fine. It's okay. It kind of works. If you have terabytes of data, this is starting to get pretty rough. And if you have petabytes, yikes, forget about it. This is just not feasible. And this is literally what we're looking at with our climate model data. So the Pangeo community was like, this is not good. What can we do about it? And they came up with this model, which is very familiar to many of us. But it's using the cloud. So we store our data in object storage in a cloud. We bring our compute next to the data, so also in the cloud, where we can access that data very quickly, in a performant way. We can do all of our analysis in the cloud. And then the only thing that we have to download at the end is our final figure or our final table. Basically, once you've done all of the computation that you want, you just download the final result. And that's usually quite small and very doable. So me as a user, I'm using my laptop. I use my browser, I'm using a Jupyter Hub through a browser. So it's very easy for any operating system to use. And it provides this really wonderful framework. So this was kind of my introduction to Pangeo, and I was like, oh my gosh, that's so amazing. And that is how I'm able to do my work. And then I transitioned everything into this kind of cloud-enabled science. And I don't mean to say that Pangeo was the first community that did this. They're among the first in the kind of more academic research space to do this, and has had a big impact. So one example that I'll share with, I'm saying, oh, this is all great. Now we have this cloud infrastructure, and we can process more data, which is great, and that enables a lot of science. But it not only kind of makes our science faster and helps us to do the science, it also changes how we can even think about what science we can even do. So this is an example actually that I experienced. So as I've mentioned, I was using high resolution climate model data in my postdoc. So in my postdoc, I was starting to do some work. I was then talking to someone who I'd worked with in my PhD. And this person was saying, oh, what's your project? So I explained it. We're looking at, the global ocean temperature variance. And they said, oh, cool. So which region are you going to look at? And I said, oh, I'm actually planning to look at do a global analysis. And they said, oh, okay. So you mean you'll look at the North Pacific, you'll look at the Southern Ocean, you'll also look at the North Atlantic. And I was like, oh, no, I don't think you understand. I'm doing a full global analysis. Now, the reason why this person didn't understand is because what you see here on the left is kind of how most of our high resolution research had to be done previously, where you just choose a box because you can't process more than, a certain size box for these very high resolution climate models. And so, when I said, no, that I'm doing just the analysis on the full global ocean, I'm not choosing a region, they were like, oh, wow, well, that's amazing. And so that was the first time when I realized, like, oh my gosh, these tools are literally changing how we're thinking about what science is even possible. So anyway, so I think this is really cool. So I did say talk about the challenges as well as kind of opportunities of open science. There are a lot of challenges, and many have been mentioned. I'm just going to bring two up that I thought might be interesting. So the first is how to navigate the open science space. So this is very much in the open source. It's the same thing. How do we navigate the open source software space? This has been mentioned a little bit before. Here, what I'm going to mention is that there are starting to be more initiatives to really try and map out this space so that we can better understand this. And so I met Carlos through the Open Source Science, where we have an interest group on exactly this. And this is another kind of example of trying to create more of a map to help guide everyone, actually, scientific users and researchers, as well as software developers, to understand what the kind of software stack is that is being used. So this is an example. They're calling it the Scalable Open Source Analysis Stack. I think this is someone who's part of the Pangeo community, so it might be kind of more tailored toward the kind of climate, and this is very much for cloud-enabled science. But I think this is really interesting to me, at least, because before I'd seen this a few months ago, I hadn't really thought about how to organize all of the different packages that we're using. So here they're saying there are actually a lot of packages that are used across a lot of disciplines and communities. So you can see here for data storage. So again, this is cloud enabled. So we're talking about Czar and Parquet. Then there's the data access side. If you're using Intake, FSspec, data API. So these are some of these higher level libraries, Pandas, Xarray, the processing side. And then it's this domain specific one where they're saying this is kind of where each domain has their own packages for doing their own analysis. But then actually for the visualization and user interface, we're kind of back to some of the more community standard ones. So this was an early prototype. I think they actually have iterated on this since I grabbed this snapshot. But I thought it was really interesting of how we're grouping this together, which I think will help, especially coming from kind of a scientific user. This will really help to understand what packages that we're using and what we need to understand. And also what we can as a community contribute to. Okay, so now the next challenge, the second challenge that I'm going to mention is one that we all know and has been mentioned, but science, open source, all of this has no barriers, has no borders or no barriers. So science has no borders. It should be able to be done. Here I put kind of these global maps. It should be able to be done anywhere in the world. There are a lot of reasons why this is very tricky to do, because working with international governments, working just with the US government is very tricky. So I'm not going to go into that, but I think the same thing can be said for working across these institutions, even just within the US, as an example. So I was talking a bit about this before, so I'll kind of bring this back, and I tried to kind of figure out where, like, how OSPOs fit into this diagram that I'm making, which is, you can tell I'm not an artist, but I'm trying. And I have to say I haven't really worked with OSPOs or anyone at an OSPO yet, so this has been great here. Already I've learned a lot. So anyway, so we have these institutions that, as I mentioned before, were often quite siloed because you needed, access to University A's library subscriptions to see your journals. You needed access to that computing system, and people outside can't really get access to these, so it ends up siloing people. But one of the great things about universities or institutions or agencies, you have people who are working across all types of disciplines. And that's kind of how the university system was built, again, because you needed physical access. They wanted to have as many disciplines as they could in all of these different places around the country. So, you have people who are in the computer science department, who are in the physics department, who are in the earth science department. And that can also be a real benefit to collaborate across disciplines. So I see the OSPOs really helping to improve that. I think many of us here, well, I won't talk for anyone else. I know for me, I really didn't know about what was going on in other departments when I was at academic institutions. And that's maybe mostly on me. I could have gone and figured it out, but it's hard to do that. So I think specifically for open source, OSPOs can hopefully really help to bring these communities together. We've been talking about this. Let's have an academic conference, you know, like, but university campuses, I think, are a great place to really work across disciplines, see what tools are used, are commonly used, are in common across all of these disciplines. And then, of course, also if we have OSPOs at a lot of these institutions, they can improve the communication across institution and between institutions. So I think that's kind of where I see OSPOs fitting into this diagram that I started. But I still think it's really important that we keep all of these open science, open source communities that are cutting across. And this is where I think this actually could be really fruitful if we get use the universities as places to see what's common across discipline. But then when there are really specific technical questions, especially that really need to be focused by discipline, by data type, by types of analysis, that's where the open science communities come in and they kind of fit across. So this is kind of how I'm thinking of the current kind of landscape of how this works. I'm not sure how well I explained it or if you agree. And if you don't, that's great. We should talk about it. So yeah. Oh yeah. I forgot one more thing. So kind of as an example to this, I guess it's more of a caution to make sure that we're not siloing ourselves or letting branding be a barrier to the science that we're doing. And I think this idea of kind of branding is what might make this structure a little bit harder to do. So this is a very specific example that I have noticed personally. And by branding, I kind of mean, you know, I'll use NASA as an example. You know, NASA is a funding agency, but it also gets funding from the White House, from the federal government. And so every year we do have to say, oh, this is what NASA's done. We, you know, still deserve lots of funding from the federal government. And so as a result, a lot of, and this is not just at the funding agency level, it's kind of at all of these levels, people always want to have the branding to say, we did this, you know, so we want money for this. And which makes sense. So it's maybe very naive of me to think that we could get away from that. But I think in many ways, this is a real barrier to doing science openly. So my example of this is I've used Jupyter Hubs a lot. I did all my postdoc work on the cloud using Jupyter Hubs. The Pangeo Jupyter Hub was the first one that I started with, and it kind of allowed anyone in ocean sciences to use it for free. So free computing, free access to the cloud stored data. And what we've kind of seen since then is a lot of organizations like NASA, NOAA, USGS are like, this is awesome. We're going to do the same thing, but for our institution. So now we have NASA Jupyter Hubs to access the NASA data. We have USGS Jupyter Hubs to access the USGS data, and so on. And there's nothing inherently wrong with that. And maybe that's a good first step. But I'm just seeing the same kind of silos that we had when we had HPC systems at institutions. It's not really getting the full benefit, I think, of using cloud. So this example, like my vision, I guess, is that I don't want to have to know who made the data set and which Jupyter Hub to log into to access that data. As a user, I don't want to have to know these things. So I don't want to have to know that Landsat is a joint operation between NASA and USGS. So it's a great satellite. I don't want to have to know who is running that. I don't want to have to know that Sentinel is joint between NASA and the European Space Agency, or that CESM, which is this climate model, is based at NCAR. I shouldn't have to know all of that. And I especially shouldn't have to know which cloud region these data sets are stored in, so that I can make sure that I'm not, you know, having too big of an egress cost or anything like that. So as a user, I just want to be able to click the button. Maybe I say, I'm going to use Landsat data. It'll take me to the right place that's optimized for cost, for performance. Maybe there are parameters that I could set. I say I want the cheapest way to do this. It'll take me there. I can do my analysis, and I don't have to know these things. So, but for this to happen, it means we need a lot of coordination across a lot of places that will be very, very difficult. And it really means we kind of have to overhaul how we measure success and give credit for things. So, okay, I think that's actually where I'm ending. So I think this year is really a spark that we need to keep working together in the future. So maybe this year is the year of open science, but it's just the launching pad for all of the years to come. So anyway, I'm very excited for this. I always like to end with some nice NASA images because so these are these inspirational statements. Keep supporting open source and open science. Thanks for all of your contributions that you all do. And thank you for having me here.
Ready to time, but still some time for questions.
So I guess the idea of not creating silos of whether compute or data is definitely an admirable goal, and somewhere I think that we should go. Do you or has NASA thought any bit on, I guess, how do we balance that with security? Because obviously, like, if a whole bunch of universities have their own computing machines, but that's also, you know, limiting the scope of potential attacks to just their unruly students, or, you know, kind of the people who have access to each individual one.
Yeah, I mean, that's a great question. I actually don't know. NASA really values security. I don't know the specifics for, in this case, for NASA. So you're right. Having a more centralized system might make it more vulnerable, or might make the risk much higher. So yes, I haven't thought, my vision hasn't quite gotten that far. I don't know all the specifics, but yeah, that is a good point.
Sure, no worries. And I mean, maybe this is something like an OSPO could work on, you know, if you're linking people's ORCID ideas to their institutional accounts, then maybe you could do cross collaboration that way, where like, if I have an OSPO that knows my ORCID idea and your institution or NASA or something also does, then that would be easier to federate, you know, an account between different places or something.
Yeah, that's a good idea. Yeah, and right, I guess, and I say, oh, anyone can just click and log in. Yeah, maybe there does have to be a kind of system. You're a vetted user, or, you know, something like that. Again, I haven't really gotten that detailed in my vision. I'm kind of pitching it and seeing what people say. So I appreciate that.
So do you see the National Science Data Fabric pilot project? Probably not, it sounds like.
Probably not.
So
yes.
Valerio Piscucci at Utah, and my connection is actually through Michaela Tauper at UT Knoxville. They're trying to build the layer across all of these different things so that you can actually find and use them all. So we're actually working on that layer right now so that all of the silos exist, because those are really domain specific things, and trying to find that what's the common thing that works for everybody. Those projects have always failed because we can never make something that's actually useful, that's generic enough to be able to handle everybody. So we're trying to say, how do we kind of bring them together in a catalog kind of form so we can still get that, I'm looking for this kind of data, where is it? And we have that global, truly global kind of catalog across all of the different science data. And then you can get a lot of what you're kind of looking at. This is obviously intended to be a long-term project, intending to cover essentially all science that the US government's funding, which is not a US effort as much as a kind of a global effort, because we have so many instruments around the world. But that might be something we should talk a little more about.
Yeah, sounds good. So that's really on the making the data, bringing the data together so it's more easily findable across all disciplines. Yeah, that's a very valiant effort. That would be great.
So there's also the Access effort, right? It's the successor organization of XSEED. And I just found out about that like a few days ago when I was preparing some of the things for this conference. And it's basically just, XSEED is like this amazing organization that was, I think, coming out of Indiana University mostly, but then, you know, it was sunset and then replaced by a new organization. And the new organization seems to be much more focused on data sets. And so they provide, you know, you can basically instantiate petabyte scale pods, data pods, and they have all the same way of accessing the data, and then there's a whole bunch of metadata that needs to be generated. And I'm sure that as you have that infrastructure available, which is, by the way, not dependent on any of the commercial clouds, so there's no egress cost, right? So that will actually allow to create sort of new forms of data exchanges, data discovery, but they all, have like these startup struggles from what I've heard, where people don't really know about them yet. And yeah, you go.
Yeah. Well, I was just going to say, like, Access and the Jetstream project, they don't brand themselves super well. I have friends who work on the project, and definitely as far as like the Department of Energy, NASA, and like NSF, like we don't talk as much as we should. So this is a really good point, because you end up creating very similar works across the different funding institutions.
Yeah, and then I think that also the tool sets, right, that map that you show, they're not necessarily cognizant of those ecosystems, right? And so then their services don't really support that tool set. And so then that creates difficulties, right? So I think there's a really interesting conversation of like adapting. And I'm sure the people who are, really want to, their goal in these funded projects is adoption, right? And they would do anything that they can to get this infrastructure widely adopted, because that's the metric of success. So I think there is, I'm surprised how much people are sort of focusing on the use of the commercial cloud. If there are all these other infrastructures available, and there's just not the right communication coming along yet.
Yeah, communication is very difficult.
So we should
never be.
And I think that the picture that you really quickly, the picture that you draw with the OSPOs, University A, University Agency, and Institute. I would also add a column industry.
Absolutely, I agree.
Right, and because I think that's super important, and I think that we know, for instance, especially in data analysis, a lot of investment into very highly valued data analysis tools comes from the financial industry, right? Who basically use the same tools, and so that's I think should take advantage of that.
Yeah, great.
One other great time about one of the questions.
You said when you were a postdoc, you discovered the benefits of cloud computing infrastructure. You have to use a massive database and a lot of compute resources and so on. To me, the elephant in the room, that the problem that Carlos is trying to solve is that supporting software is expensive and someone has to pay the bill. And so where does the money come from? So I'm wondering, how did you pay your share of the Amazon bill for your research, or did you? And is whatever you did to pay for that scalable to the bigger question that this conference is trying to answer?
Yeah, good question. I personally did not. It was a grant through my advisor, which paid for the cloud compute. And the grant through the Pangeo community was paying for the data storage. So Pangeo started basically like, well, let's see, this is a pilot program. We're going to put a lot of money into this and see if it works. So the data storage side was set. So that was just through a research grant. I said, we want, to use this for, although it was a research grant through the Moore Foundation. So it was not government funded, which meant it had more.
The maintenance of the software that you use, which I guess is the kind of core thing here, was funded how, do you think? Well,
I used a lot of different software. The postdoc group I was in was actually a mix of software developers and research scientists. So some of the software I was using, the main one being Xarray. We had some of the core developers in my group, in this climate data science group. And this was also kind of meant to be a pilot of how, can we work better together? Where me as a researcher, I'm like, whoa, this is really confusing. And the developer can be like, oh, cool. Like, how would that be easier? So that was really, really great for me. But they were also being paid through this Moore Foundation grant. So I don't know if that's scalable. It was getting, a limited amount of, a few years of funding, just as we all do. But they, my advisor did get the funding to do that. So yeah, I didn't talk a lot about some of the funding side, but we all know philanthropies are really, I think, leading the charge in enabling a lot of open source.
I think, the federal government has, created funding structures for like commercial cloud use, right? So there's the NSF has the cloud bank.
Yep.
And I think it's not only
One
NSF, but it's also.
that works.
Huh?
Yeah, so I took out the slide that listed some of our funding.
Yeah.
That's one of the ones that probably won't make it out before the end of this year. But yeah, we're starting to try and get more of those at NASA too, that are just specifically targeted at open source and open infrastructure in science.
Yes.
Yeah, a lot of the software I relied on is, as we all know, from volunteers.
But there's a significant funding set aside by the federal government into what they call cyber infrastructure, right? And that's basically maintaining open software, making sure it succeeds, making sure they have like maintainers, right? But they don't know the specifics, right? So one of the things that happen right now is they're looking for models, right? And I think some of the models maybe we invent, right? That how do you make this sustainable? The government is not interested to just pay for that forever. They want to actually get something that can sustain itself over time, right? And then
actually,
focus on.
I will actually pitch to all of you and kind of suggest to all of you. There are kind of two sides that I find in government. You get these like great, solicitations that are like, yeah, we want to support open source in this way. We're looking for proposals, but then you also get the other side where you have people more from the research community submit. They're like, yeah, we're going to, develop this code or, make this great project. And the reviewers don't know what that means. And are like, this isn't science. And they review it poorly. This does happen. And we are working on it. So my suggestion to all of you is if you're interested in being a reviewer for any grant proposals, that would be great because we desperately need more people who have the technical expertise, and especially in the open space, you can say, yeah, this makes sense. This is, well written. So that would be really great if if you want to do that. So yeah, let me know and I can pass that along. And that I think would be a huge way to support more funding getting given to these communities.